Welcome students. We want to discuss about area between curves in polar coordinate setup. So let's see, why do we need a polar coordinate setup? So consider the following equation: x square plus y square minus x the whole square equals to x square plus y square. This represents the cardioid. So the shape of the cardioid is this. Yeah. So this is a cardioid. Yeah. Question: how do we find the area inside this? So how to find area enclosed by this? Now, generally what we do is we integrate y dx, say from a to b, depending what the interval is. But the equation of y and x, so y is related to x in an implicit way, and this is the implicit equation of the function. And you can already see it would be difficult to separate y in terms of x. So it will be difficult to write y as a function of x. Yeah. And also it will be only done locally because y is not completely a function of x, right? So there's upper part, there's lower part. So this problem becomes already difficult in Cartesian coordinate system. However, the same cardioid has a nice representation in terms of polar coordinates, where r equals to 1 plus cos theta. So now this representation is nice, and we are hoping that we can find out the area enclosed by this cardioid using polar coordinates. Here is the verification of what I said. So you can see that if you look at this equation here, the graph is given by this equation. All right, so let's do the same thing and draw. So I'm going to stop this, make it invisible, and draw 1 plus cos theta. And you see it's the same graph, right? So you see red and blue graphs are overlapping with each other. So your cardioid has a simpler representation in terms of polar coordinates. So we need now a mechanism on how to find the area under the curve using polar coordinates. So let's embark on that journey. So recall, if we have a circle of radius r, let r be the radius of circle, and if this angle is theta, then basically the area of this sector, so area of this sector is going to be area of sector of the circle is half r square theta. Yeah. So essentially, I mean, one can think about it in the following way. Area of circle is pi r square if the radius is r. Pi r square. And if we want theta radians. We want the theta slice. So we want theta radians out of 2 pi total radians. Right? So in that case, it will be what? So we are going to take theta slice. So theta slice of this. So then in that case, we get theta over 2 pi of pi r square, which is pi and pi will cancel. You have half theta r square or r square theta. Okay. So this is the underlying idea behind finding the area of the sector. Now we will basically see, suppose we have a function r equals to f of theta. So this is how usually a polar curve is represented. And we want essentially the function. So we want the area So suppose we have R equals to f of theta from angle A to B. So where theta goes from A to B. So in this case, you have a polar curve which looks like that, and then we have this angle B, theta equals to A, and this angle is theta equals to B. So these are the angles. What we'll do is now we want to find out this area. So we want to find out this area here. Yeah. To find out this area. So how do we go about it? So what we'll do is we will try to use the approximation using the sector. So we'll do the following. We have a small slice here. And we want to find out area of this slice. And then we'll sum all the area up, similar to the idea of Riemann sum. So suppose if this angle is delta theta I, we have this is R, the function is R equals to f of theta, delta theta I, and this area is going to be, so area delta AI. Now we have R here, right? We have R1, there may be a different radius here and different radius here, right? So what we can think about them is we can approximately think that they are the same, of same length. So since Ri's are small, so this area is going to be half. Let's call this as Ri, and we'll think that this is also approximately same as Ri. So area is going to be half Ri square theta, because we are approximately thinking about this as a slice of circle. We're thinking about it as a sector in a circle by approximation. Okay. So now what do we get in that case? We have delta theta I is half Ri square theta I. So therefore, what is the total area? So total area is going to be summation I going from 1 to n half Ri square delta theta. Delta theta here. Because the angle is delta theta I, so half Ri square delta theta I. Similarly, here also we'll have half Ri square delta theta I. So this is the area. This is an approximation, and you get the accurate area by taking limit as n goes to infinity. Now note that what is Ri? You have R equals to f of theta. You can think about Ri as summation I going from 1 to n half Ri can be thought of as f of theta I. So this square delta theta I. Now we can just think about this. So if you look at this, this corresponds to the integral really. So this is integral A to B half f of theta square d theta. All right. And another notation for the same thing is half integral A to B r square d theta, where it's clear that r is a function of theta. So it's exactly the same setup like polar coordinates, sorry, like rectangular coordinates. Okay. So this is the area in the polar coordinate. So let's formalize this. So a region A of a polar area A of a polar region is given by A to B half f of theta square d theta. And it's often written as integral A to B half r square d theta. Okay, so again, what is the setup? The setup is you have a polar curve, which is given like that. So this is the r equals to f of theta. Now note that theta is an angle, so it ranges from So this angle is A and this angle is B, and you are interested in this region, the area of this region. And this is the formula for it. So now let's look at one example. So sketch the cardioid R equals to 1 plus cos theta and find the area that it encloses. Okay, so let's sketch the graph. So first of all, let's understand how do we draw this. So we have cos theta. So note that if I have to draw cos x, the cos x graph looks like this. So we have cos 0 is 1, then it is 0 at pi by 2, minus 1 at 3, minus 1 at pi, at 3 pi by 2 it's 0, and then we get back again at 2 pi. So this is 2 pi, this is pi by 2, this is pi, this angle is 0. So this is how cos x looks like. Now cos of x plus 1 or 1 plus cos x is going to be shift of this. So again, we draw the same curve, or I can draw it here with a different color. So it's going to be a shift up. So this is how 1 plus cos x looks like. All right, we are drawing this in Cartesian coordinate. Now we want to draw the polar. So in polar setup, what you do is you measure r. Your r is 1 plus cos theta. So let's draw that part. So we have, so again, you're drawing the polar coordinate, but you're drawing in xy plane, right? So let's start. When theta is 0, so when theta is 0, r is equal to 2. So when theta is 0, so this corresponds to theta equals to 0. In your case, in that case, r is 2. After that, the value of r, which is 1 plus cos theta, declines to become 1 at pi by 2. So the value r, so here the and is the this is the theta increase direction, right? So the theta, so you have r starts decreasing. So the value of r is the distance from the origin. So this starts decreasing. Yeah. So it starts decreasing and it becomes at pi by 2, it becomes 1. So note that it starts decreasing and becomes 1. Yeah. So what is r? You're measuring r as the distance from the origin, right? Yeah. So these are the representative points. Yeah. As you keep changing angle, you get points, and r basically becomes what? R becomes at this, the value becomes at pi by 2, the value becomes 1. After that, the value of r starts decreasing, still decreases until pi. So it's still decreasing until pi, the value becomes 0, right? Note that the angle here is, so this is how you're measuring the angle. Say angle here is pi by 2, and then the total angle here is going to be pi. Okay, so let me erase some part of it because we're going to keep it, use it to draw, find the area as well. So, and then by the symmetry of it, or otherwise you can see that then it starts increasing from 0, sorry, from pi. This is, here we are at pi. And then after that, after pi, it starts increasing, becomes 1 at 3 pi by, so becomes 1 at 3 pi by 2. And then again, it increases the value at, to make it what? 2. Now note that r is the distance from the origin, right? So it's not x or y. So you're not going negative here. All right, that's something we should be sure about. Okay, so here's our cardioid, and now, so we have drawn our cardioid successfully. Now we want to basically find out the area enclosed by it. So how do we go about it? So first things first, we'll exploit the symmetry to make this problem slightly simpler. Exploit the symmetry. Note that you don't necessarily need to exploit the symmetry. So the area is the cardioid A, area is 2 times the shaded area. And what is the formula for shaded area? So half, again, so 2 outside. What is the, now I need to write down the integral for this. Note the angle is changing from where to where. Here the angle was 0, and then it became pi here. So it's going to be 0 to pi half r square theta. Okay, that is important, or half f of theta square. So 1 plus cos theta square d theta. Yeah, okay. So 2 times this guy. Now our problem has simplified to be able to find the integral, which is given by the following. So that 2 and 2 can neutralize each other. You get, this is going to be integral of 0 to pi 1 plus cos theta the whole square, which is going to be 1 plus cos square theta plus 2 cos theta d theta. Now we know how to integrate 2 cos theta, but cos square theta we need to change it using double angle formula. So we have 0 to pi, this is going to be 1 plus, now note that we have cos square theta is cos is 1 plus, is basically 1 plus cos 2 theta divided by 2. So we get, in this case, we get 1 plus cos 2 theta divided by 2 plus 2 cos theta d theta. Now we can simplify it a bit. So we can write 0 to pi 1 plus 1 by 2 is going to be 3 by 2 plus cos 2 theta divided by 2 plus 2 cos theta d theta. Now we can integrate. So we get 3 by 2 theta. So integration of cos theta is sine theta. So we have sine 2 theta divided by 2 times 2. So it's going to be 4. All right. So that is, and then here we get 2 sine theta. And the limits of integration are 0 to pi. Now note that when you put pi in sine or 0 in sine, it becomes all of these will be 0 essentially. So when we substitute, so let's see, we get what? We get, when you put pi, you get 3 by 2 pi plus, now sine of 2 pi is 0, so this is 0, plus sine of pi is also 0, so upper limit minus the lower limit. When you put 0, you get 3 by 2 times 0, sine 0 is 0, so 0 plus 2 times 0, again 0. So the answer is 3 by 2 pi. So we managed to find out the area, the total area of the cardioid. So this is how we find out area of a cardioid. Okay, so let's move on to the next problem now. Now again, consider the cardioid from the previous example and the circle centered at origin with area equal to that of cardioid. Find the area inside the cardioid but outside the circle. So area inside the cardioid, which is, and outside the circle. So this is the area we are interested in. So let's use a different color pen so that it's clear. So this is the area we are interested in. So how do we find out this area? Well, first of all, we need to compute these intersections, right? Where do they intersect? So how do we go about it? So first of all, what is the area of the circle? So it says the circle centered at origin with area equal to same of the cardioid. So area of circle which is pi r square, is same as the area of the cardioid, which we got from here. So when you equate this, you get r. So you can cancel pi, you get r square equals to 3/2, or we get, so this is your area of circle, this is the area of cardioid, right? So we have r square equals to this, or this implies r equals to root 3/2. So we have found out. So again, so what are we doing here? Let's write down the steps. So we have step 1, we are going to integrate with respect to theta, Then we found out the intersection points. Point of circle, and so circle and the cardioid. So equation of circle, the formula for the circle is r equals to root 3/2, and we need equation of cardioid. So equation of cardioid, which is r equals to 1 plus cos theta, right? So now we have equation of circle in hand. This is the equation of circle, Now we need to compute the intersection. So let's compute the intersection. So the intersection is given by intersection. So intersection is given by 1 plus, so we'll equate r. So we have 1 plus cos theta equals to root 3/2. So this implies cos theta equals to root 3/2 minus 1, which turns out to be roughly 0.225, or theta in radians is 1.344 radians. Now again, I did this computation using a calculator. Okay. Now we want to find out area of the shaded region. So let's see. So and then we'll exploit the symmetry, and exploiting the symmetry would basically mean that we will basically be interested in this area. Yeah, and we'll declare that it's 2 times the area of that, right? So the angle is changing from, where's the angle changing from? Angle is changing from 0 to this angle, which is 1.344 radians. So how will the area look like? So we have area is area A equals to 2 times the shaded region above x-axis, right? So we are talking about this area here, shaded in this light green color. And we have, this is going to be 2 times the shaded region. So what is the area of the shaded region? So we have first the area of cardioid minus the area of circle. All right, because this, if I integrate just the outermost, it will give me the whole part, but then I have to remove the cardioid part, the equation, the area gotten by the circle from it. So let's see. So this is going to be 2 times area of the cardioid, we have 1.344 half 1 plus cos theta the whole square d theta. And out of this area, I'm removing 0 to 1.344. Equation of circle. Equation of circle is what? R equals to root 3 by 2. So it's going to be half root 3 by 2 the whole square d theta. Now from here, you can get the general formula, right? So now let's work it out. So this is going to be 2 outside. So you can bring the half inside. So it will be what? It will be 0 to 1.344, 1 plus cos theta the whole square minus 3 by 2 d theta. I'm combining this to integral because this will give you an idea about how to deal with this problem in generality. Now we have already expanded this, previously computed, but with different limits, right? So this is going to be, I'm going to use the same expansion I did last time. So we had, when we integrated this, 3 by 2 plus 2 sine theta plus 1 by 4 sine of 4 theta, right? We had, let's see, is it correct? We had 3 by 2 theta sine 2 theta by 4 and 2 sine theta. So 3 by 2 theta here plus 2 sine theta plus 1 by 4 sine theta. And integral of this part is going to be 3 by 2 theta. And then we have 0 to 1.344. And then again, when we substitute the upper limit minus lower limit, we get 3 by, so note that this 3 by 2 and this 3 by 2 will cancel out. Okay, so this becomes twice of sine 1.344 plus 1 by 4 sine of 2.688 minus, when you put 0, they are all 0, right? So 0 plus 0. And this, when you use a calculator, is going to be 2.0581. So this is the area, right? So this is the area of the cardioid that's outside the circle. Yeah. Thank you for your attention.